All right, so this is we call this an interactive panel, as though that's something special, but actually it is, because you're going to drive the conversation in the room and also in Twitter. And, we're going to have, for the first 15 people who ask questions in the room, but not out there, sorry, you're going to get a free book. You'll see what it is when it comes to you. But it's not C++ 11, I'm sorry. They haven't written that yet. So this panel is called The Importance of Being Native. Obviously, most of you probably already kind of understand what that could mean, but I think it's actually an interesting topic that it would be nice to hear from all of today's speakers about, why is it important? So if C++ is the answer, what's the question? We're going to start with, who wants to start? The man in the middle? Herb? The man in the middle.
I'll take it. Okay. The simplest answer to that is something has to talk to hardware. Not everything can be a virtual machine. Somebody has to write the virtual machines. That's the most fundamental question. Secondly, we have a lot of applications that require performance and compactness, and only down near the hardware with compact data structures and sort of fairly raw performance can you do these things. I mean, we're doing streaming video. That's not that easy to write in a super high level language. Also, once you get sort of virtual machines upon virtual machines, it limits what you can run under, and you also get problems with what your correctness really is, because the systems get too complicated. I like static type checking because it's harder to make really fundamental blunders. It's easier to catch a lot of errors so that you can concentrate on the problems that remain. And so the dynamic typing languages, I think, can disguise errors for too long. And so that's, I think, my fundamental issue. Something has to be at the hardware level. Something has to deliver with performance. And I like the static type checking.
Andre?
Herb?
So we're going to just pass it along.
Let me broaden your question a little bit to if C and C++ are the answer, what's the question? What kinds of languages do you need to build a civilization built on software? You need native languages. There is no substitute. You can build managed languages on top of them, but you can't build the second floor without the foundation. It just can't be done. This is the question specifically, then more narrowly, if C++ is the answer, what is the question? My view of it is the most important thing you can notice about the way our civilization is built on software is that it's inherently layers, and you can call them abstraction, you can use all the highfalutin names, but it's layers that build other layers, that build other layers, because it's impossible to build any program of any significant size without a subroutine, or as in the Turing tar pit. You have to have small libraries that then you can build bigger libraries, that you can build bigger libraries, and that's what we've done. And people complain that our computers today, which are supposed to be 1,000 times faster, run the word processor just as fast as our 1980s computer running WordPerfect. However, you get more. You cannot build large complex systems, even like Siri or like telecom infrastructure and other kinds of things, without these layers of abstraction. So the layers of abstraction are necessary. The best you can do is optimize how many of them there are, but you can't get rid of them. They're necessary because we have no other way of building big software. C++ is the answer to the question, how do you make that as cost-free as possible? How do you reduce the cost of those layers of abstraction? Because you're going to have them. You need to then make them as efficient as possible, especially to the ones that matter the most for performance and efficiency.
If I can come back and follow up on that, C was very good for writing relatively small programs very close to the hardware, but I felt I couldn't organize my code, I couldn't express the abstractions, and so came up with the notion of zero-cost abstraction to be able to to build these more complicated systems.
And that's the key question. How do you build those complicated systems with efficient abstraction? That's the answer is C++ is the king of that today.
One of the nice things is that every time you add a layer of abstraction, it's not always putting you further away from the hardware. Sometimes, if the abstraction is very good, it can actually reach down and bring you closer to the hardware than you would have otherwise thought possible. Like, take a std copy. A copy is a range of elements to a destination, and it could be arbitrary elements from an arbitrary range, like a std list or whatever, linked list. But the library can go and say, oh, if your source is contiguous, if it's vector or if it's a std array or C array pointers, and I see that your elements are like integers or chars, then I don't need to do the element-wise assignment. I can just call memmove or memcopy in some cases. And that can expand in the CRT, which is a layer of abstraction below, to a special sequence of assembly instructions that just blast the bits from the source to the destination faster than any handwritten code could. And yes, someone theoretically writing C, a gigantic program from scratch, could put memmoves and memcopies in all the right places. But to get a library to do that automatically for you is, I think, really powerful.
Excellent. Hans, you want to say something?
Yeah, sort of getting back to the original question about trade-offs between native and virtual machine-based languages. But I've actually been on both sides of this, and my impression is sort of a little bit in contrast to what others have said here, is that the trade-offs are very often subtle, and it's sort of hard to talk in generalities. I mean, there are Java virtual machines that are largely built in Java, the JIKES Research VM and things like that. On the other hand, there are also there are also often reasons why you don't want to live in that kind of world. If you want to build a particularly compact application, my experience is that that's often not a very good place to live. It's also generally not a good environment in which to build very short-lived applications, for example, because at least in my experience now, which now dates back a few years, it's very difficult to get very difficult to get reasonable startup overhead in those environments if you don't already have the VM running. So there are trade-offs, and in some of those worlds, there's some things that just aren't very expressible, and as a result, you end up being slower. The performance just doesn't end up being there, but I have a hard time sort of coming up with a big generality of why you should prefer one over the other.
Andre, what about you? I mean, besides the fact that you can use templates.
First, I agree with what everybody else said. Second, let me actually refer back to Bjarne and my conversation of yesterday, which I think was very revealing. Again, this kind of great alignment in opinions. We're talking about this frictionless abstraction, which we both like a lot. And I think when I think of C++, this comes to mind: frictionless costless abstraction. So you can actually build layers that actually don't add much overhead. Unlike many other languages in which, as Bjarne told me yesterday, you can actually, the inliner with heroic efforts can actually inline and essentially wipe away a couple of indirections, a few indirections, up to a number of indirections. But the style of programming espoused by very high-level languages inevitably is going to rely on a bankrupt memory model, on a very high-level abstraction that is not reflected in the hardware, and is going to essentially use through and through inefficient constructs that then the compiler must map to hardware. And one great thing about C++ is that essentially it does map to hardware in a very natural way. And I personally like that. I don't like to imagine that there's no arrays, because the memory is an array. Okay, I don't like to imagine there's no arrays, so you have to use trees. The trees are your arrays. So we're building a world on a foundation that there's an impedance mismatch, right? So you must imagine that the memory is a list. You must imagine that memory is a hash table. Or you must imagine that the memory is an object, right? The memory is a huge array, and it's great that you can actually take a chunk of it and use it. So this is great. Costless abstraction. This is what I love about C++.
Yeah. Can I just make one concrete example? We talk so abstractly. I mean, take the simple point is that a good small function being inlined ends up being faster and smaller because it's smaller than the function preamble. And so you save type and space. And that's the key to things like all of these parameterized STL functions. The individual operations like incrementing an iterator on a list or a vector, or the less than operator for simple comparison functions, they become individual instructions. And you get a program that's both smaller and faster. So by raising the level of abstraction, you can, when you find a nice sweet spot and you do it right and all of these things, you get an abstraction, as you pointed out, is higher yet faster and closer to the hardware than the original.
Excellent. So any questions? Perfect. Let's go to this one since it's closest to you. And he gets a book. It's just a nursery rhyme.
So back in November, whenever Microsoft announced at the Build conference that there were going to be not as many C++ 11 features in the next release of Visual C, there was a very strong reaction by many C++.
The word trader was thrown around?
Yes, trader and other things. And we could rehash those things. But I'm interested in what's the feel so far from .NET developers about this shift sort of in focus and priorities on native code for the platform going future?
So a couple of things. So the question about the C++ 11 and conformance and stuff, hold that thought. Let's talk tomorrow morning. Speaking more about what about .NET developers, what do they think? Well, first of all, .NET developers not out of a job. Anybody who thinks that .NET does everything or that C++ does everything wasn't listening to Bjarne, or isn't living in the same world we inhabit and is going to discover that, because each optimizes for different things and each have a role and should be continued to supported. Java falls in that managed group. Having said that, the most frequent category of email I get about C++ training and information is from people saying, where can I go to find a good white paper on how to use modern C++ 11 for Java and C# developers? That tells me a lot. I get a lot of those emails. Would somebody like to write that? Somebody needs to.
Hello. I'm working on that. And the first cut, which is not the tutorial, but it's the introduction, is exactly the paper version of what I did today. And that is live in IEEE Computers, the January issue. So you can go and read an I think an 8-page paper hitting the highlights I was hitting today. It is not a training program, but if you want the ideas, it's down on paper. I'm doing a similar kind of effort for an academic conference in Estonia, of all places, in March. That's written and coming. Same kind of idea. Hit the main models for how you do things, the main ideas, and carry on. Trying to get out of the mode that you have to start with an array, and then you take a couple of pointers, then you take a couple of macros to control the mesh you're in, and in 3 years you get to something that's so advanced that nobody can figure out how to do it, like a sort template. It's completely backwards.
I was hoping you were going to say not Estonia, but Elbonia. That's the
Too much mud this time of year.
Do you remember the pig?
the pig in yeah.
The Elbonia.
Take that offline.
Yes.
So let's take this question from Twitter, because we haven't been getting enough of these for some reason. But
there's been a few.
So can we expect support for modules in TR2 as has been hinted? And is it going to take 5 years?
Bjarne, do you want to start?
Bjarne.
I'll start. There's 2 questions there. I am a little bit worried that the modules proposal we have is not quite well enough thought out. Everybody wants modules, but it's rare to find 3 people that don't have about 4 opinions between them about what a module is and what problems modules solve. So I am not so sure if it'll come in a TR or on the next version of the C++. The real question, which we're going to spend most of the next week talking about at the standards meeting, is what's going to happen in the 5-year time scale. And I hope to see a lot of libraries and a few little things. And I'm on record saying that we can handle at most one big thing. The question is whether we are able to agree on one thing. I don't know.
Bjarne mentioned this, but actually our next standards meeting, some of you may know, it starts in 4 days, on Monday in Hawaii. So almost all the speakers today and tomorrow are going to get on a plane over the weekend and go there and then work in windowless rooms all week, really.
Yes.
And
hiding from the sun's deadly ultraviolet radiation.
Until midnight.
We know that you don't believe this, but we're going to spend 5 days working hard in a windowless room in Hawaii.
Moving right on before we sound too defensive about it. The interesting thing to me about modules, I agree with Bjarne. I think there's something there. I do not believe that the proposals we've seen so far have quite got it yet. However, this goes back to C++'s strength. How many of you have had the joy of having a C++ class definition in a header file, everything nicely defined, all the functions defined, out of line, and then you had to add a private member function and recompiled the world? How many of you have enjoyed that? Now, why? There is no language reason, because that private method, there are a few pathological cases, like maybe it could affect overload resolution. They're not realistic. They never come up. But because you can't call that function anyway as an outside user, right? However, this is fundamental to C++, because it is essential for C++ to be what it is, that the compiler can see the full definition of a class, including its data and functions. Because it is that, the fact that the layout of a class is exposed not to the programmer, but to the compiler at all times, which is the heart of C++ optimizability. That is why you need a different kind of class, or you need to do a pimple kind of idiom if you want to hide representation really. Because you have to forcibly decouple it. Because C++ is all about making sure you have access to that for optimization first. Even though you're protected in the language, but the compiler has to be able to see it. We had better not lose that with modules. So that's where that's related to modules.
Great. Go, Stefan. Okay.
I've often wondered when writing, pimples, if, one reason people sometimes write them is just for, faster build times. But, it would be nice if you could just flip a switch and say, okay, now I want to remove the pimple and just have all the data members right there instead of a layer of indirection and release my shipping code.
But then other people use it so that they don't have to recompile when they change the implementation and change the data layout, which is, if you gave them a choice, you would lose that interchangeability, which is somebody else's main reason for modules. And then there's people that want modules for dynamic linking. There's a lot.
I see a question for Hans coming in from the interwebs.
So what effect do zero-length bit fields have on data rests?
Well, we switched topics here quite a bit. That one has a short answer. I think that's that one has a short answer, which is that they separate sequences of bit fields into multiple memory locations, so you can prevent accesses to one part of the sequence interfering with accesses to the other.
Excellent. All right. So as promised, this is interactive. You're right here. Bartosz, we'll get to you.
Okay. So my question is related a bit about templates, because I see all these great new features and I'm like a kid with a new toy and I can hardly wait to try them all out. But
is he related to you?
No, amazingly. Not after what I'm going to say. So my question is that on most of the projects I've worked on, and even at work, people are very afraid of templates. And while the template system is really powerful, and in fact, I think it's actually Turing complete, most people don't use them. So I see this great new feature, which is variadic templates, and I wonder who's going to use them, because people were afraid of templates already, but now they're going to be because they're all like, who's going to maintain this? So what was the reason actually? And that actually leads me to the fundamental question. Was this great effort in bringing variadic templates more about providing support for huge libraries which are maintained either by huge corporations or by in very huge communities like the GCC ones? Or can the average Joe be encouraged to use them? Like me, for instance.
I'd like to say this one, something about this. Templates are really, really important in modern C++. And the statement that nobody is writing them is just flat wrong. Now, there are people who don't write them. I mean, for all I know, there may be 1 million people that don't write them, but that still means there's a couple of million that do. So let's not overgeneralize this. Secondly, there is a great temptation to demonstrate the most complicated and most advanced template features, and some of us are more guilty of that than others. And you shouldn't let them scare you. If you write simple templates, you can get simple effects. And by the time it starts looking hairy, stop. Don't ship stuff that you feel uncomfortable with, but don't be afraid of templates, because most of us has a threshold that will allow something. There's nothing particularly wrong with a vector or a sort function. The code for a good sort is simpler than the equivalent for qsort.
Remember, when you saw Stefan's talk before, this is the viewpoint of an STL implementer. When you saw Andre, it was the point of view of someone who probably knows more about variadic templates than anybody in the world.
I forgot more about variadic templates.
he forgot more about variadic templates than most of you knew about templates in the first place.
And what they say is extremely interesting and gives you insights to the depths if you're a very advanced or really want to know what's going on. And you can mostly ignore it and just use C++. And their talks are very, very good and very, very important, and that's why we're recording them and making them live on demand, but they should be labeled # not safe for work. Because there's a little bit too much, if we shouldn't be too interested in only that little glorious complexity. It's good to know about, but using it is actually not nearly as complex. For instance, Stefan, you gave several rules.
Yeah.
If you follow these rules, you can ignore the next 10 slides. Remember that part of the talk too.
Just auto, throw it there.
And just using the STL or another quality library is much, much easier than to write the code yourself, at least if you want to deliver quality code. And I distinguish rather sharply between code to be delivered, where you have to be more cautious, more conservative and such, and code you do for experimentation or because it's fun.
Now, having
and
said
it's
that,
an important distinction.
Having said that, these guys are going to write libraries that use this stuff that's going to make your life easier, and you'll never even see it. And that's a real powerful tool that C++ gives us, is the ability to write powerful libraries.
Except for the War and Peace written by the error messages.
No, that was only an Oscar Wilde play.
Oh, Oscar Wilde
much
is
shorter.
briefer. Yeah,
People are so scared of template error messages. I love them because that means it stops stuff before it ever gets shipped to users. Like I would rather have a 100-line template error than the simplest null dereference because I can catch the template error on my machine.
Whenever I use GCC, I say G++ compile type head. I just get the first line. That's what I care about.
All right, let's move on to another question.
Oh yeah. Okay, let's so we'll do this one, that one, this one. This is great.
And there's some good ones down there.
And over here, we need more mics.
I think I saw one.
Go ahead, Bart.
but I didn't see.
Okay, so we've been doing concurrent programming for some time using pthreads, using Windows threads, and so on. So I'm really happy that finally C++ and C caught up with concurrent programming.
It only took till the 21st century.
Yeah, but it seems to me like it's already behind by, I don't know, 5 years or 10 years. because right now we have all these powerful multi-cores, and the programming of multi-cores really should not be based on threads. It should be task-based, right?
Yes.
And Microsoft has the PPL library and so on. And this is totally not reflected in the C++ standard. Is there?
There's stood future.
Are there? Are there plans?
Let me take a first shot. Have you seen the mailing for the papers we're going to start considering on Monday?
No.
So I'll talk a little bit tomorrow in my talk, but in particular, one of the things you'll see there, so first of all, it's important to standardize existing practice, not novelty. We're not always so great at that, but it's useful before you make it an international treaty to know that it works, and so threads and mutexes are certainly appropriate. One of the papers you will see is a pure library-based proposal, an initial proposal, which the committee will have to see if they like it and then maybe work on more to refine over time, but on continuations. So future.then, non-blocking, which is extremely important, right? As a pure library. There is another paper that says, okay, if you have this as a pure library, what would it take to do C# await in C++, in standard C++? And that paper is authored by one of the designers of await. So we're catching up fast. C++ is moving fast.
Okay. And also the programming of GPUs, for instance, that requires you to learn a completely different language, CUDA. And of course there is AMP. But it's still very much behind.
I mean, in some sense, standardization has to lag behind like the absolute frontier, because once it gets into the standard for C++, it lives basically forever. And while they're still trying to figure out, I mean, that's one reason why it's useful to have libraries like Boost. They, hashed out the design of, Boost shared putter and Boost regex, and then, the standard was behind. But once it gets in now, the design of shared putter is baked in stone forever. So.
And a lot of these things involve difficult technical questions, which often aren't apparent before it hits the standards committee. So we actually had a lot of discussions about task-based parallelism and the like in the last cycle. But one of the problems was that we kept coming up with issues that we didn't really, that either weren't adequately addressed, or at least we didn't know of any work that addressed them correctly. So, for example, the interaction between threads and thread local variables is kind of a tricky thing to think about. And you can't really put it in a standard without having some answer to this, and we didn't. So that was one reason it got postponed.
So the only thing I'm afraid of is that the standard could be locked into threads and sort of make it very difficult to move to task-based programming.
I think that's completely wrong.
Okay.
And that's all I'm going to say about that. What we lay down is a foundation for further concurrency. That is, whatever else you have to have an abstraction of the thread of concurrency down by the hardware. If you want a task-based system, look at what we did with the async and futures. That's an example of what you can do on top of threads and locks. So the threads and locks system is the worst way of doing things, except for the fact that it's completely universal. We must do it.
You can't build a thread pool without threads,
etc.
But it goes the other way around too, because, for instance, in this release of Visual C++ that's now about to come out, we're implementing stood async, stood future, as well as thread mutex and everything, but specifically async and future build on the PPL, the parallel patterns library that you just talked about. So look at the details, but that's the place to look, where it's actually not as far apart as you might think.
And the committee is very, very careful to phrase things such that implementers have freedom to do smarter things.
But there is a fundamental problem that we can't do very much about. When you compare something like C++ against just about anything else that you care to compare it against, you're comparing a resource-less committee that has to define something that works for all systems against usually a proprietary, well-founded organization with a marketing machine focusing on a very specific smaller section of the market. So they have more resources and less complexity, less constraints on what they can do. And if they screw up, They'll just sell you the replacement and make more money. And the lack of resources and the lack of being able to throw things away and say, oops, is very fundamental to the problems that the C++ standard and the C++ language has faced from day one. I mean, I made a mistake. I should have shipped C++ 1.0 with bad libraries half a year later. I couldn't ship them with good libraries, so I shipped them. But I didn't get people into the habit of building it. We don't have an organization that produces these large libraries because they take real serious engineering work to do it. And that is really hard. And that is C++'s weakness. The strength is, in 10 years' time, your C++ programs from today will work on the computers that haven't been invented today. This is not true for just about any other system. How many Visual Basic programmers are here? Does it run today? Does your 15-year-old programs run today?
Next question.
So that kind of is interesting. It relates to the question I wanted to ask, Bartosz. You asked about concurrency. Herb, you talked about modules, and you're saying our C++ programs are going to work in 10 years. What are the big unsolved problems that you guys are thinking about in terms of C++ for it to really be viable in 10 years? I think it will be, but I think there's going to be changes that are necessary. What do you think is the biggest thing, and it may be different for each of you, that needs to get solved?
Can I actually, since we have other questions, can I push that on the queue for tomorrow morning?
Yes.
Thank you.
Over here. Or whoever has the mic that's over here, sorry. This is great, but we can't put things
Excellent
up that we
question.
walk up to for fire reasons.
Wouldn't it be nice to have like a test suite for the compilers, which would verify compliance?
There are companies that sell that.
You can buy them.
They're all too happy to sell you that.
Perennial, Plum Hall.
We have several of them checked into Visual Studio, and I'm sure GCC and the others run that.
Okay.
They are incredibly picky. You change one data member, and they see the signature changing, and they freak out.
And the way they're made is that they're actually documented with this test program tests this clause dot subclause dot paragraph dot sentence in the standard.
And there's an interesting point here. They want money for them because they're costly, difficult, and boring to make. And nobody in the sort of the open source is just willing to do that kind of work. And secondly, it's not really the standards committee's job to start competing with successful commercial companies that actually does a good job. So, problem solved.
Okay, the next question over here. Sorry, I'm going to be more aggressive.
You mentioned GPU computation before in one of the other questions. How does that relate to the memory model? I mean, you were describing a memory model that's very much a shared memory model between all the different sort of tasks or threads. How would that work when you start having a more heterogeneous computing environment?
It really depends on how you program the GPU. From what I've seen, I mean, at least my understanding is that at the moment, people usually use other variants of C or C++ to program those, like OpenCL. And at least last time I've looked at OpenCL, the specification is less mature than C++. I mean, there are a whole bunch of issues related to that that are addressed in C++ 11 that aren't really addressed in OpenCL. On top of that, you're right. I mean, there are all these other issues that not all memory is shared. But I mean, even if you look at shared memory issues, the things. I mean, my impression as somebody who has sort of observed this from a distance but not really used it is that there's still a fair amount of work to be done in making that actually all work together and ideally consistent with C++ 11.
Do you see that being something that I guess the standards committee is interested in pursuing? I know there's like C++ AMP from Microsoft and these other initiatives. Is that something that you think the community is likely to rally around?
I happen to think that I know of at least one pretty good solution, but until millions of people have used it, I would not want to submit it for standardization. If pressures are such that it should be, fine. but we really should be conservative and not be too much at the bleeding edge. We should standardize what we know works. And give it another couple of years and we'll know a lot more about it. Hardware right there especially is in motion, in very fast motion right now. And you can look at it and think you've come up with a model that can pretty much take it and can all the directions it might go. But there's no harm in waiting a year or two to make sure before you shoot your one bullet and then you have to live with it in the standard and it's broken.
Well, let's go to this question here.
Yes, besides the improvement to the language, I want to ask about marketing. Besides this conference, is there any plan to help us developers to promote C++ in our companies, to try to regain all the terrain that we have lost?
C++ does not have, never had a marketing organization. It would be nice if we had more active users group. In England they have ACCU, which almost went the way of previous efforts. That is, they get generalized and to all kinds of object-oriented or C-like languages, and then there's no C++ forum left. But the C++ community doesn't have a center. It doesn't have a really active organization to support it, and I don't see where it comes from except from users getting together and doing it. It's not something you want the big corporations to do for you. If there really is an active, genuine user group, it can probably start taking money from at least 3 corporate sources. If you take it from 1, you're dead. So somebody do it, but it's not something you can expect somebody like us to do.
Okay, we're going where it's pointed right there.
There's one over here.
There's one over here? All right. So we have one that's been waiting for a while there. Then we have one there. I see you, David, right?
And there's Twitter, too.
And then this is great. So at some point, maybe people are just going to have to start screaming. The mic is going to be complex.
Well, your last question, what about Boost as far as organizations or user organizations are concerned? What do you think about that?
Boost is a very specialized organization.
They're library developers. They're, yeah.
Go ahead and ask right there.
Speaking about the future of C++, taking a look back over the last decade, which I think Herb called the lost decade, or something like that in one of his talks. I recall that one of the marketed advantages of managed code was that you had garbage collection, and you were able to not have circular references, and a number of issues were sidestepped because you had this managed environment. But that always seems strange to me because there are many native implementations of garbage collectors, and they seem, from what I can tell, to have fairly good performance characteristics. I was wondering if you could talk a little bit about your thoughts about where we're going with the garbage collection in C++, seeing that certain other languages like Google's Go now have some garbage collection in them.
So there actually was a plan to add more complete support for garbage collection into C++ 11. It ended up getting partially dropped. So the current state of affairs is that there is actually support in C++ 11 that allows vendors to provide garbage collected implementations. I don't know of any vendor that has announced a plan to do so, but it's now standard conforming to do so, whereas in the past that wasn't clear. So in that sense, it's making progress. My guess would be at this point that we're going to have to see some vendors actually taking advantage of that before it really moves forward beyond that. But I'm not sure. I mean, officially the extended proposal was delayed rather than dropped during the last cycle, and so probably Bjarne or Herb can say more authoritatively.
Yeah. We have an interface designed mostly by Hans and friends, which allows efficient conservative garbage collection of C++. You plug it in, and there are implementations, I believe, that does that. But I think that garbage collection is not as critical for C++ as it is for many of the other languages. We just don't generate that much garbage unless you sort of adopt unless you adopt some kind of Java-like style where everything is on the free store and you have a lot of pointers lying around, if you do that, you will leak, and you'll probably also have exception problems. I think that Java in particular was a huge marketing machine, and it hit the existing languages where it could. And the unsafety of some of the C facilities, the apparent lack of portability, and then they needed something to show they were good at, and they picked on garbage collection, which they needed anyway, and since they were not very efficient in the first place, the relative overhead was smaller. And so I don't feel the great need for garbage collection to the extent that the managed languages do.
Okay, right up there.
One thing I would like to see in garbage collection, and we should talk about this over dinner in Cohenahans, is, for the reasons you said, it's not as important in C++. We have shared putter, unique putter, there's some overheads there. We have other disciplines. We can actually say this object has another by value and connect their lifetimes. That's so powerful. Connecting to scopes, so powerful. However, if you are trying to implement a lock-free data structure, for example, such as a singly linked list, you really, really want garbage collection for your nodes. You can still destroy the widgets in the nodes, but you really want automatic garbage collection. So what I would love to see for future C++, which I think is actually we should work on, that it's actually very simple to specify, I think, and you can probably do it in a page or two, is leave C++ the way it is. It's not like let's garbage collect everything, leave everything exactly the way it is, but add a function which, we call it gcalloc or something, which returns you a pointer that you know you never need to delete. You opt in. Now I can implement portable lock-free data structures way better than I can do today, and way more efficiently and faster. But I'll still only use it a small amount of the time. Yeah. But when I need it, I really need it.
I agree with that need, and I definitely have been consistently supportive of getting optional garbage collection into C++, what's sometimes called litter collection, because sometimes programs do leak, especially if they have a lot of C-style code in there. I think we just have to be careful. C++ is will never become a garbage collected language that just allows you to be very casual about your objects and let them leak and have the garbage collector collect them, because that doesn't handle the resource management problem. And it is inherently inefficient compared to the AII kind of stuff. Furthermore, with move semantics, we remove one of the major convenience features of garbage collection, which is you can make an object here and I can hand it over to you, and it'll disappear sooner or later. Here, I make an object and I give him the handle. I don't even need a pointer. So the needs are still going down.
So the performance trade-offs here are complicated, especially with shared pointer. There are certainly reasons to garbage collect rather than to use shared pointer.
By the way, when I want that gcalloc, I do not want that to be conservative. I want that to be accurate, because I need the guarantee it will be deleted. So let's have dinner and talk about it.
So I had a question about I posed the question a couple of years ago when Mr. Strostrup was in Vancouver. My question was, so this standard is improving code portability, but is there anything being done on the binary level? Because I see it's a big obstacle. You have these objects, whatever, multi-dimensional models that you build, and then at the end you want to be portable, and then you flatten all that into one C. Basically, that's the only option you have if you really want to share your good work, and without disclosing your source. So is there any effort being done? And I see that is a big problem, because if you really, a lot of people work backwards to say, okay, this is my API, I have to give, and then why should I bother even using some advanced or C++ features? But eventually I have to give this C flat model or API out. So is anything being done on that? Because I think it's a big problem even for adoption of C++ and where C++ is now.
It's always been a problem. Binary interfaces are the property of the platform owners, and the compiler vendors and platform owners have by and large not been able to agree on that. Everybody wants their own layout, their own compilers, compatibility with their own code bases. It's a really hard problem. Maybe it could have been solved in 1984, but I don't think it could have been solved after that. And I don't see any efforts that likely succeed. There was a major effort for the Itanium API, and some people are following that, but not to the point of getting compatibility. Maybe some of these guys know more about these efforts, but this is a long-standing problem that cannot be addressed at the language level.
Well, actually, the scale of the problem becomes larger now because we're more interested in putting together systems residing on several machines, and every company that's busy with that kind of stuff has its own proprietary, more or less proprietary. At Facebook, we use Thrift, which is open source. Google has its own. Essentially, every company that is in the business of doing large-scale computing must solve this issue of essentially services communicating. Corba has essentially just disappeared, and COM is now sort of experiencing some revival, which is a good thing, but it's sort of Windows-specific. But essentially, I think this problem is not only about linking together binary ABI-compatible shared libraries and such, as much as how about we have entire programs living in possibly distinct memory spaces and actually on distinct strata infrastructures communicate with each other. So I hope solutions are gonna come about and be standardized.
Hey, you're on an elevator with a bunch of C++ developers. What functionality or feature of C++ 11 would you want to share with them before they got off on the second floor?
Shared putter.
Is that it?
That's it. Vector number one, shared putter number two. I don't know about everybody else. What do you guys think?
It's interesting. I wouldn't have shared pointer on my top 10.
Really? Auto putter?
No. It's still a pointer.
Yeah, that's true.
Even unique pointer is not the thing. I mean, people use far too many pointers.
I guess tuple's like better.
Lambdas.
There we go.
They change everything, and then you find three more cases they change.
Great. Over here.
So the topic of the session is supposed to be how good C++ is at mapping down to what is natively happening at the hardware. However, I see at least one big glaring place where it falls down on this that Herb has a really good talk on is around the internet on memory latency and how it doesn't actually expose memory latency. So if you look at an instruction on C++, you're not sure how long that thing is going to take. So I understand the hardware is a moving target sort of view on the world. It's really hard to say and pin down, okay, this is what we can do.
Well,
for this.
there's two parts to that.
But there are two places I think actually that it's not going to move. One, we know the speed of light. We know locality is going to matter. Two, we know SIMD, SIMT, something like that is really, really efficient at using transistors. So what can we do basically to give that native feel to C++ in those regards?
So a couple of things. First of all, a lot of that's language neutral. That's why that talk about machine architecture is language neutral. It's about any language. Right. Because you could be writing assembler x86 move, and you have no idea if that's going to be a single cycle or if it's going to be hundreds or millions of cycles. You have no idea, right? So this is irrespective of language. What we could maybe add, I'd love to see somebody propose being able to portably talk about alignment and to deal with false sharing, to be able to talk about cache lines in a portable way. That would be actually useful because that's a performance-oriented topic that you want to know for performance-oriented reasons. As far as SIMD, SIMT, and those kinds of things, that segues into GPU architectures. Run, don't walk, please, to Welcome to the Jungle. It's on the front of my blog, and that gives a summary of some of the issues involved, especially memory architectures.
Also, go. Also, as far as SIMD goes, you've got instructions like SSE2 or whatever. Some compilers can auto-vectorize plain old code, that's looping over an array with indices and say, oh, I just see you're doing a floating point multiply. Okay, there's a special assembly instruction that I can embed and light up those dark transistors, and that's actually shipping in VC11. So, in addition to other compilers.
One of the big benefits I actually see of putting something like this into a language in these two regards is it actually makes programmers who are more novice think about these sort of things.
Right.
I've made so much out of my career in just going to a programmer and going, so have you thought about cache misses? And they go, what?
If you
make them think about it, there seems to be a lot of value in that.
I think the average programmer, the mythical average programmer, will make a total hash of that. And I think dragging your code to the assembly level to get the last bit of efficiency out of your current architecture is a complete losing strategy. In the real high-end thing, they have computer science PhDs and physics PhDs doing nothing but porting applications from the one architecture to another. And when they're finished, the next architecture comes along. If you take the average student, the average developer, and teach them to write concurrency at the assembly level, you're dead meat. We have to get higher, not lower. We have to have the compilers and runtime systems smarter, not relying so much on the programmers. And we are running out of programmers who can do that job well because the number of systems that has to deal with concurrency is growing faster than our ability to educate good people that can understand it. And as a matter of fact, I am not at all sure that the new crops of programmers are in any way better than the older crops because they've been taught a little bit about concurrency, but they've been taught it at a more superficial level because there's so much else they have to know. Security, various forms of machine learning, graphics, and you find that the average student does not know his machine architecture, he does not know his algorithms, and he does not know compiler architectures. So let's not go there. This is a very dangerous place, and we don't have the infrastructure to deal with a solution along those lines.
May I add some? I agree with Herb. I disagree with Stefan, and I disagree with Bjarne, which is like.
I thought I was agreeing with them. Anyway,
that was about something else.
Yeah, I know, but I disagree. So that makes it a bit difficult, a bit tense here. So there's multiple facets to this issue. So number one, yes, the pipe dream of how many cycles it takes to execute anything has been shattered by the first pipelined machine, right? Here's a play on words, right? So the pipe dream, first pipeline machine essentially complicated things so much it's impossible to predict anything. So right now researchers, what they do, they use simulators. You can't sit down and look at a program running through an analyzer and know exactly how many cycles it's going to take. It's so the models are so complex; it's virtually impossible to predict anything exactly. So there are simulators that do that. All right. Number two, I think the approach. Incidentally, I've been involved in this. I think the approach of opportunistic optimizations, the kind of Stefan mentioned, I disagree. I don't think opportunistic turning whenever possible the hamburger into a cow is good. I don't think it's good because
they can turn it into about 10% of a cow. So
right, so
like the hooves.
It's not a good image to keep in your mind as you're having dinner. Okay. So it turns out that this sort of opportunistic optimization is sort of dangerous because there's going to be people who are going to assume it, rely on it, and you change a comma and it falls off a performance cliff, and what the hell is going on? Number three, Bjarne is totally right that this is an issue that you don't want to expose that kind of low-level information. On the other hand, there's a domain that is filled up with people who don't have PhDs, yet they do want high performance. What would that be? gaming, my friends. There's not a lot of PhDs, and actually the best gamer there is, he does have a degree, right? So I had more vacation than the guy had school, but he's so much better at everything that he does than I could ever be, right? Carmack, right? So essentially, there's a field that essentially does need to rely on such things. And GCC, it does add the __ vector thing, which actually aligns things for, lays out data in an aligned manner, good for SIMD operations. So there's two trends. Trend number one, you can count on increasingly fewer things, right? Pipeline machines, complex architecture, deeper cache hierarchies, new memories. There's going to be a memory. Maybe locality is not going to be an issue in 10 years. Maybe it's like, locality is locality.
Locality is always getting more important.
We're going to put neutrino
You were right until that sentence.
I listen while you talk. Give me a second here, okay? So it is not impossible that new hardware kinds are going to make certain issues that are today vital irrelevant. And definitely they're going to have their own issues. With that, you come with what do we expose here? Do we expose the SIMD operations? Are they here to stay or not? I think that the jury is still out. I don't think it's. I don't think we can say do this one way or do the other way.
Now, having said that, remember the picture. The fundamental picture is always all these layers. The first few of which are hardware, cache hierarchies, pipelines, and everything. Then you get to low-level OS services, BIOS OS. Then you get higher-level frameworks. Blah 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 blah. By wonderful design, you can reduce the number of layers a bit by good design. Yeah, a lot of them are fatter than they need to be, but good design will only reduce them. It will not eliminate them. You need those abstractions because every layer increases 10 or 100-fold what you can express. Otherwise, we can't build big software. You do not want to pierce through those layers because the abstraction is what gives you the ability to write big software. So I think what Bjarne is saying is do not drill through and say, and be aware of everything down there because people's heads will explode. No one will be able to write code that way. It'll just slow us down too much. However, here's the Zen question. When does adding a layer of abstraction make your code faster? And the short answer is when it lets you declare intent.
Yeah.
And then your tools know what you're trying to do. They can enforce it at the language level, at the tools level. They can optimize it because they know what's going on. And that's why you'll see things like DeclSpec of Vector and C++ AMP lets you say with only one language extension restrict, I want to be able to run on different kinds of processors.
Let me
but you just need to give the surface, it is a fine art to surface just the right few knobs, not the 100 you could, that together orthogonally cover the whole space and work together. That's a high art.
Let me give a concrete example. When we write code and we think serially, we use something like find. And find finds the first element of a data structure. If we are writing concurrent stuff, we don't want find. We want find all. That finds all the occurrences of something or all these things that matches a predicate or something like that. So one way of raising the level while at the same time, that is raising the abstraction level, while at the same time improving performance, is to provide concurrent algorithms that expresses, as it was, the intent. But it's not just the intent, it's not just an annotation, it's a different algorithm.
Yes.
And if I spawn something find all, I get a lot of answers back. And that's what I really want.
And you want them asynchronously, by the way.
Yes.
Yes. Well, there's another find.
But the point is that there's a lot of them. But the point I'm trying to make is that if you want to make concurrency explicit, you do it by making algorithms that allows you, composable algorithms that allows you to express the intent of doing things in parallel potentially to people, and then let the runtime system and compilers implement that intent.
I'll give you two specific examples that are exactly what you said. So if you have find all, and by the way, you might want find any, which is you only want one, but you don't care which one, then you get the early termination. That's often important. So let's say you have find all, find any. Today, we had better not spell them find all, find any, because that you might have find all, find any as sequential algorithms, and you could pass it a predicate with side effects, right? and it would be wrong to parallelize. So today you say you want parallel underscore find underscore all, parallel underscore find underscore any, right? So that's what we want today. Now imagine you had a language feature that said, by the way, this predicate is a pure function.
Pure.
Now I can internally parallelize plain find all, find any, because I know it's safe. And the user didn't have to say a thing other than this completely concurrency, apparently unrelated thing. My predicate has no side effects. That's one of the few things you need to bubble up and have as a lever in the language.
The importance of being pure. Right.
Excellent. All right, let's get a question there while you can.
I think one of the most interesting sort of annotation-related things.
No, I'm not going to interrupt STL.
One of the most interesting annotation-related things is I think R-value references. Because compilers knew for decades, really, when things were R-values, but programmers could never really get a handle on that, even in the libraries. And then when that was added to the language, this extremely important fact that some object in a program was not visible to the rest of the program became available for libraries to exploit. And programmers didn't have to do anything to add those annotations. It's just the language had to become smarter so that libraries could access that information and go, steal resources from it. So if people had to go annotate everything with std_move, it would have been far less successful.
Well, they have to annotate with double ampersand, right?
Oh, no, they don't. You return by value, my friend.
Yeah, there's a special bit of standardese. Just don't return double ampersand.
So I'm coming from the perspective that C++ is the language that I want to use to exploit my hardware to its maximum potential. And with the introduction of atomic types and atomic integers specifically, it seems like we finally have the ability to do concurrent data structures in a somewhat standardized way. But along with that, we don't have any control, and this was brought up in the earlier question, over things like alignment. Now, the compiler knows what alignment is optimal for any given platform. That's how it generates optimal code. Does it seem like, or is there a proposal to add a little more alignment control instead of specifying strict alignment, like 16 bytes, but optimal for the platform?
There is alignment control in C++ 11. Presumably you want something a little bit beyond that. It's like do the right thing, or just optimize.
Right.
There's no proposal at this point.
/ do the right thing.
Feel free to submit a proposal to the committee. And 4,000 something.
There is some alignment control, so
I mean,
could use that creatively.
You can control alignment, but there's nobody that knows what's optimal in the current system. I have not thought of it deeply enough to know whether it can actually be possible to say just do the right thing.
The other problem there is often, especially in the presence of concurrency, when you care about alignment, it's to avoid false sharing. And for that, you really want to know the cache line size, and that's not something that's normally defined as part of the processor architecture. So even when when the compiler is generating code, you might not know what the right number is yet, which complicates the issue.
Because it's not the processor, it's whatever the memory subsystem is and the cache system that happens to be attached to on that piece of end-user hardware.
It's
quick, while you can.
Right.
Quick.
I have a question about C++ and kernel space, and I'm just wondering, are kernels suitable to be written in C++, or is that primarily something that C is just better for?
Of course, C++ is much better for kernel work than C. I mean, who would be stupid enough to say otherwise?
In this room.
There's actually a switch that I don't know if we're documenting it yet, but it's been implemented called /kernel that actually makes C++ better for kernel mode. It turns off certain things and warns, I believe, or errors if you try to use things like RTTI that are problematic. But
it's like the hard real-time stuff. There's just things you shouldn't do. And just because you can do them doesn't mean that C++ gets unsuitable for it. Just like there's things you shouldn't do in C in a kernel, just don't do it.
I'll bet that the requirements for kernels are a lot like the requirements for safety critical systems like Joint Strike Fighter.
The most problematic thing, I believe, for kernel mode, I'm so far away from being a kernel programmer, but I hear things, is like even things like templates that you would think would be very innocent because they compile to nothing. They still generate code. And I believe kernel programmers care deeply about whether code is pageable or not pageable and which page goes in or something. And that's one of the things this /kernel switch, and I think we've got a decal spec as well, allows you to control.
any hard real-time, any close to the hardware embedded system stuff, you cannot just know the language and expect miracles. You have to know, if you're doing things like that, safety critical stuff, you must know your language, your hardware, and the mapping between them. If you lose that contact, you're in deep trouble. C++ allows you to have that context. It also allows you to write lousy programs where you lose touch with everything. Don't do the latter if you're in a safety critical environment. Or if you're in a kernel, because it might actually be used for something safety critical. Better work.
But by the way, it's so important, and this has come up several times, to remember that C++, modern C++, has a happy path through it, where it is clean, safe, fast, and easy to use. Use make shared and shared putter. Use auto. Just do it. Now, when you want that extra 10%, 1% performance, C++ always lets you open the hood. It ain't locked. The key is left in the hood. You can always open it and go deep. But you only do that when you actually need to. And that's how you get the best of both worlds. And so some of the talks today have been way down there. Then much of the C++ code people should be taught to write are up here, while knowing this is available if they need it. Break in case of emergency.
Even if you want to go down and do the really low-level stuff, usually the right way is to provide yourself a little interface to the low-level stuff that is type-safe and all the good stuff, and maybe a very thin layer of templates that allows you to write notation and maybe generates embedded assembler or whatever it is takes to go down there. But I don't think you should take the low-level stuff and spread it throughout your code and make that the primary interface to your users.
My opinion about the original question is, I've seen some kernel code, I know some kernel programmers. It's a mix of perception and reality, in my opinion. The perception aspect is definitely important. Kernel programmer really wants to know. So you look at the kernel code, you pretty much know. You if you squint a little, see the assembly generator. You pretty much know. That being said, there are macros and C style abstractions that people use that would be actually easier and just as efficient with C++ facilities. For a kernel programmer, I think the issue is I think that the essential issue is exceptions. So that's an absolute maybe, right? So that's an absolute issue that people have. Like, do I enable exceptions or not? Because the moment you enable exceptions, even if you don't use anything, what's going to happen is you're going to have a drop in performance.
Well,
I didn't say anything while you were talking, okay? So you're going to have a drop in performance. It's measurable, okay? And again, here the perception comes into play, and people say, oh, so I enable exceptions. Things are going to be less efficient, bigger, and everything. The reality is with the exceptions, the startup and the entry and exit sequence of functions tends to be bigger, larger. And there's no reasonable way to avoid that easily, because the compiler must assume that any opaque function may throw, even if it's a C function. So there's going to be more constraints on the optimizer, more pressure on the code generator. It's gonna be more difficult to generate good code from exception-enabled, let's say, C, right? So this is sort of a mix of perception and reality. That being said, I do think that a good kernel programmer could actually use C++ gamefully because you want to have a good kernel, you want to maintain it, you want it to not have many lines of code. And to be honest, a lot of kernel code is incredibly boring and repetitive and asinine code that could actually be done much. I mean, imagine you want to have a hash table in kernel. I mean, you have to have arrays and lists and whatnot. And the way people have to do them over and over again with with selects and var clause and and the juju and all that stuff, it's just not all that good, right?
Okay.
Destroy me.
Anyway, so yes, I disagree with some of what you said. I don't think performance is necessarily decreased by exceptions. It is obvious that there are certain optimizations that can't be done, but I think a lot of that is overrated, and I think that the current implementations of exception handling may actually not be optimized for kernel work, we might actually have to look at the implementation of that. Clearly, there has to be restrictions of what you do inside a kernel. When you look at exceptions in kernel as an issue, you have to see what is the alternative, which is very pervasive testing of error conditions and error returns, which also costs things. But anyway, I would think you can't throw exception-throwing code into kernel code that already exists and doesn't use exceptions, because they're a mess of pointers already, and it doesn't work. So if you wanted to use exceptions, you'd have to more or less engineer a new kernel from scratch. Now, the rest of C++ is an obvious candidate. I think some of the more negative comments about C++ in kernel space has come from people who suffer the delusion that a good C++ is huge class hierarchies where every operation is a virtual function. That's not kernel code. There are things in the kernel where an abstract class is a beautiful interface to it, but I mean, huge trees with hierarchies with everything in it is not the way you would organize the code. And I think some of the comments about C++ negative comments in kernel base, comes from people who believe it has to be truly object-oriented to get any benefits, which is wrong, or they think that templates necessarily bloat. They don't, if you know what you're doing, or that you must throw exceptions left, right, and center, which you don't have to. It's a very specialized domain, just like writing a signal code for a signal processing chip is. It's not the same as writing a web app. One of my key points is that there are different domains with different requirements. C++ happens to be useful in those domains, but you have to know what is the appropriate style for the domain you're working at.
By the way, the cost of exceptions, for example, on our 32-bit compiler, it's the fat expense of the cost when you turn it on, even if you don't throw a kind of model you set. On our 64-bit compiler, it's pretty sweet.
It's table-based, yeah. And GCC has
Table-based
that
means
on
there's a
x86
table, right?
and x64.
Oh, yeah. Table-based means there is a table, which means it's
But they can put that in a cold section.
I know. I'm talking about zero overhead exceptions.
It bloats code size, but
if you don't throw.
Hold on.
Yeah, in the non-throwing case.
Zero overhead exceptions add overhead because they put pressure on the code generator and the optimizer. They can't generate code as freely as they could otherwise.
But you don't know how significant that is.
I measured 7% on some code I tried.
Did you remember to check every error condition in the alternative case and take all of those tests out in the exception case?
My code doesn't have bugs, Bjarne.
then you don't need exceptions. It's very simple.
All right, we have time for one more question.
We have one right here. How about this one right
I'm
here?
kind of curious.
Enough of that.
That's a tomorrow question.
That's tomorrow. Oh yeah, that's right. Okay. Tomorrow question.
According to you.
So I'm kind of curious about what your guys' thinking is with regards to event loop programming, which kind of is related to kernels because that tends to be event loop based programming. But specific and first, I just want to say thank you so much for bringing async and lambdas and futures. Definitely a step in the right direction, but for us, we do quite a bit of event loop programming, and one of the things that would be great for that is like a coroutine-like facility, kind of like Lambda's call CC, if you guys are familiar with that. And I just was wondering if there was sort of any thoughts or plans on adding that sort of facility to C++, or has it been determined to be kind of too difficult to implement?
We're going to consider a proposal on that on Tuesday.
Oh, okay. Great. So, but it's not part of C++ 11.
We're going to consider it at the standards meeting for C++ Next on Tuesday.
Yeah. What C++ 11 has is stood function, which allows you to save actions to execute later. But it's not like a function that can be paused and then resumed. So, I mean, you could write that by hand.
Yeah. And that's the proposal I was talking about with resumable functions that is similar to C# await. By the way, how many of you C++ programmers who know about C# await have ever had C# await envy and wished you had it in C++? Yeah, I get that a lot.
So you said earlier that you can open up the hood
for kernel-based programming and get to the lower levels. The question I had was, it doesn't actually seem to be possible today, and it's becoming really difficult for a whole bunch of code that I end up interacting with that is not able to use exceptions, because you have things like standard move and standard forward and pair and tuple that are extremely useful without exceptions, but cannot be used because you can't filter the includes to exclude the things that are going to throw exceptions. And it's just a simple library design problem where you just need to be able to tell it that you don't want standard string. And that maybe you want a version of standard pointer that just ends up empty if allocation fails instead of throwing. And there's just no way to express that.
There's an undocumented and unsupported macro in SQL that shuts up exceptions that maybe we should support someday. It's called has exception 0. Seriously,
Yeah.
don't use it because we don't test it. But
that one shuts them up. It doesn't omit them. I don't.
No, it really omits them. All the throws, they're if-deft out.
Okay, it means different thing than what I'm saying. I'm saying I don't want standard vector to actually be there.
Oh, yeah.
Because
There
it
you would
throws.
want things refactored. And
The problem here is very difficult, because if you start filtering out features you like or don't like, you fracture the language community each time you do that. So you want to, and if you ever mix the code where one piece of code responds to an error with an error message and something else with an exception, somewhere in your system you have to something that handles both. Now, if you take another feature like runtime, like dynamic cast, you can get another fracture, and you get an exploding set of dialects. So it's a very hard problem to solve. I don't hold out hope for that. Non-standard for a specific area, do it, but don't expect the standards committee to do it, because there's that explosion.
I'm going to throw a time expired exception because we have to get you on the bus. The buses are here. We got to wind down. Thank you for asking questions.